Calculus with parametric equations. If we have a curve in parametric form with x of t and y of t, we want to calculate the slope of the tangent curve at various t values. So we want dy dx as a function of t. So let's take a look at where the formula for that comes from. To find a formula for dy dx that involves the parameter t, we're going to get this from the chain rule. If we have y depends on x and x depends on t, then from the chain rule, we have dy dt is equal to dy dx times dx dt. Now here's another way to look at this if this is a bit confusing. What we're saying is we're taking the derivative with respect to t of y, which is a function of x, but x is a function of t. So here, how would we take the derivative of this? We would take the derivative of y with respect to x, so that's y prime of x, times the derivative of the inside, that's x prime of t. Well, y prime of x, that's dy dx, and x prime of t, that's dx dt. So we have this equation, and what we're going to do is we're going to solve it for dy dx. So if I solve for dy dx by dividing by dx dt, we're going to get this equation. Dy dx is equal to dy dt all over dx dt. So this is a formula for finding the derivative, calculating the slope of the tangent curve if we're given a set of parametric equations. To find dy dx, we find dy dt over dx dt. Now we can also find the second derivative. For the second derivative, we get the second derivative of y with respect to x is equal to, well, it's equal to the derivative with respect to x of dy dx, right? So we take the derivative of the first derivative. But in terms of the variable t, what we're going to have to do is find the derivative with respect to t of dy dx, that first derivative, over dx dt. And this one's not very intuitive to students. Just to give you a brief idea of where this comes from, I want to think about dy dx as y prime. So this step right here, we can think about as dy prime dx. And from the chain rule, dy prime dx is the same as dy prime dt, the derivative of y prime with respect to t, times the derivative of t with respect to x. And so how do we go from here to here? Y prime was dy dx, so this first part is d dt of y prime. And then over, instead of multiplying by dt dx, I can divide by the reciprocal dx dt. So there it is, d dt of y prime is dy dx, and then over dx dt. So it's really just a chain rule, doesn't quite look like it. So we're going to need to use this formula to find the second derivative given parametric equations. To recap, derivatives of parametric equations. If we have a curve in parametric form with x of t and y of t given, then dy dx is equal to dy dt over dx dt. And the second derivative of y with respect to x is d dt of dy dx all over dx dt. So let's apply it to this example. Given x of t equals e to the 2t and y of t equals t squared minus 1, find a, the first derivative, dy dx, and b, the second derivative of y with respect to x. For part A, to find dy dx, we're going to find d dt of y, which is t squared minus 1, and then d dt of x, which is e to the 2t. Well, the derivative of t squared minus 1 is 2t. The derivative of e to the 2t is 2e to the 2t from the chain rule. The 2's will reduce down to 1, so we get t over e to the 2t as our dy dx. And now for part B, if I want to go ahead and find the second derivative, that's going to be d dt of dy dx. So dy dx we found in part A was t over e to the 2t. And so it's important to simplify our dy dx as much as possible before moving on over here. And then all over dx dt. So that's d dt of our x function. Our x function was e to the 2t. All right, so this is going to be a little uglier. Here, I'm going to go ahead and do the quotient rule. So in the numerator, I'm going to have the bottom function, e to the 2t, times the derivative of t, 1, so we have low d high, minus the top function t, times the derivative of the bottom, so that was a chain rule, 2e to the 2t. So minus high d low, and then all over the bottom squared, e to the 2t squared. So that is this whole top derivative. And then the derivative of e to the 2t by the chain rule is 2e to the 2t. So let's go ahead and simplify as much as we can here. So in the numerator of the numerator, so here, I can factor out an e to the 2t up there. So we're looking at e to the 2t and then 1 minus 2t. So that's what's left, a 1 and then a minus 2t. And then we have over e to the 2t squared. And then over 2e to the 2t, but that is like over 1. So I could think about multiplying by the reciprocal, 1 over 2e to the 2t. So what we're looking at here, actually we can do a little bit of canceling now. So we can say the e to the 2t are going to cancel out there. And what I have is 1 minus 2t over 2e to the 4t. So here I multiplied the 2 and the 2t. And so this would be my simplified second derivative. In this example, I want to find the tangent line to the curve x equals t squared and y equals t cubed minus 3t when t is equal to radical 3. So I actually want an entire tangent line. So I'm going to need both a point and a slope. So to find the slope of the tangent line, I'm going to need to find dy dx. But dy dx is going to be d dt of y. So the y function is t cubed minus 3t over d dt of the x function, which is t squared. So we're going to end up with 3t squared minus 3 over 2t. So this represents the slope of the tangent line at different t values. I want the slope of the tangent line at radical 3. So I want dy dx at t equals radical 3. So let's substitute this in. 3 times radical 3 squared minus 3 over 2 rad 3. The square root of 3 squared is going to cancel, and so I'm just going to have 3 times 3, which is 9. 9 minus 3 is 6. So I have 6 over 2 rad 3, and I can divide. 2 goes into 6 3 times, so I have 3 over rad 3. And if I multiply the top and bottom by the square root of 3 to rationalize, rad 3 times rad 3 is 3. So 3, whoops. So 3, and then these 2 rad 3's cancel. So I just get a slope of rad 3. So this is the slope of the tangent line, but I also need a point on the line. So to find a point on the line, I'm going to substitute radical 3 into x and y. So I need the point that corresponds to t being radical 3. So x of rad 3 is equal to rad 3 squared. Well, that's just 3. So my coordinate point so far is going to be 3 comma something. And then y of rad 3 is going to be rad 3 cubed minus 3 times rad 3. Rad 3 cubed, so rad 3, rad 3, rad 3, that is just 3 rad 3. And then minus 3 rad 3, that's 0. So it works out quite nice. My coordinate point is 3, 0. So this is like my x1, y1, and this is my slope m. So I can plug this into point slope form of a line. Y minus y1 equals slope rad 3, x minus x1. And so my equation is y equals rad 3x minus 3 rad 3. So here is my tangent line to the curve right when t is equal to radical 3. So this happens at the coordinate point 3, 0. So if we were to sketch this tangent line, so right here at 3, 0, the line that we just found the equation of has positive slope. So it's going to be this line right here that we just found the equation of. But if you notice at the point 3, 0, there is actually another tangent line that would pass through that point, but that one would have negative slope. And so why is it possible that one point can have two tangent lines associated with it? Because of how this curve loops back around. So at time radical 3, my curve happens to be at the point 3, 0, but that just means at some other t value, I would also get to that point 3, 0. But specifically when t is equal to positive radical 3, that corresponds to when my tangent line would have this positive slope, radical 3. As a follow-up question, using the curve above, x equals t squared and y equals t cubed minus 3t, for what values of t will the tangent line be horizontal and will the tangent line be vertical? So a tangent line is horizontal when dy dx is equal to 0, and a tangent line is vertical when dy dx is undefined. So we already actually found dy dx. Dy dx was dy dt, that was 3t squared minus 3 over dx dt, which was 2t. So if we want to find when this is equal to 0, it's when the numerator is equal to 0, as long as that value doesn't make the denominator equal 0. So for the horizontal part, we're going to solve when does 3t squared minus 3 equal 0. So for this quadratic equation, I could solve it in a few different ways. I can factor out a 3 and then factor the difference of squares, or here I can go ahead and add 3 and then divide by 3. So I get t squared is equal to 1. So t is equal to plus or minus 1. So at t equals positive 1 and t equals negative 1, that's when the tangent line will be horizontal. As long as those values don't make the denominator equal 0. And we're going to see right now what does make the denominator equal 0. We're going to solve 2t equals 0. Well, that's just t equals 0 if I divide by 2. So at time 0, that's when there is a vertical tangent line. So at t equals 0, I guess we haven't explicitly been told it's time, but we always let it be t because it typically represents time. So at t equals 0, that corresponds to the coordinate point 0, 0, 0 squared, 0 cubed minus 0. There is a vertical tangent line, so that checks out. And then when t is equal to plus or minus 1, when t is equal to plus or minus 1. So at t equals positive 1, that's going to give me 1 squared, that's 1. And then 1 cubed, 1 minus 3, that's negative 2. So when t equals positive 1, that's going to be down here, actually. This is when t equals positive 1. There's a horizontal tangent line, or a line with slope 0. And then when t equals negative 1, that's the other place where there is, a horizontal tangent line. So that checks out with the graph. And now let's find the second derivative of y with respect to x for that same set of parametric equations, x equals t squared and y equals t cubed minus 3t. So we already had dy dx, that was 3t squared minus 3 over 2t. To find the second derivative, of y with respect to x, we're going to need to find d dt of that first derivative, 3t squared minus 3 over 2t, over the derivative of my x function. So the derivative of t squared. All right, so to find the derivative of this guy, this is a quotient, but I don't want to use the quotient rule. If I can avoid it, I'm going to avoid it. So here I can split this up or karate chop it and take the derivative with respect to t of, if I split this up, this is 3/2 t. So 3t squared over 2t is 3/2 t. And then minus 3/2 t to the negative 1. So 3 over 2t, I can rewrite that as 3/2 and then t to the negative 1. And then over the derivative of t squared is just 2t. So I have not yet taken the derivative of the numerator, but I will now because it's just a power rule and a power rule. So we're going to have just 3/2 plus 3 over 2 t to the negative 2, and then over 2t. So here is my second derivative, but we can do a little bit of simplifying to this, some different ways that we can do it here. I'm going to think about this as 3/2 plus 3 over 2t squared, and then all over 2t. So what I can go ahead and do to clear my fractions, I can look at the least common denominator. So I can go ahead and multiply the numerator and denominator by a 2t squared. So if I do that, if I multiply the top and bottom by 2t squared, then this is going to distribute here. And I'm going to end up with 3t squared. So the 2's are going to cancel. So I'm going to have the 3 and the t squared. Here, the 2t squareds are going to cancel. So just plus 3. And then all over 4t cubed. And then I can leave that as my final answer. In this example, let's find an equation for the line tangent to the curve x equals secant t, y equals tangent t, where t is defined between negative pi over 2 and pi over 2, at the point where t equals pi over 4, first without eliminating the parameter, and then by first eliminating the parameter. So without eliminating the parameter, what we're going to go ahead and do is find dy dx to get the slope of the tangent line. So we're looking for an equation of the tangent line. So we need a point and a slope. So dy dx, that's going to be d dt of y, of tangent t, and then over d dt of x, which is secant t. So the derivative of tangent is secant squared. The derivative of secant is secant tangent. So luckily something simplifies here. So we can cancel out a copy of secant. So we get secant t over tangent t. And we can actually simplify that a little bit further if we want to, because secant is 1 over cosine and tangent is sine over cosine. So here, what we really end up with, if we multiply by the reciprocal, so if we multiply by cosine t over sine t, the cosine t's cancel, and 1 over sine is cosecant t. So that's dy dx. I want dy dx at t equals pi over 4. So I want cosecant of pi over 4. And that's 1 over sine of pi over 4. That's 1 over radical 2. So it's just radical 2. I'm going to skip the trig here. So that is just radical 2. So this is the slope. And I also need a point. So to find the point, I'm going to need x of pi over 4 and y of pi over 4. So x of pi over 4, that's secant of pi over 4. Well, that's actually the same thing as cosecant of pi over 4 because it's 1 over cosine of pi over 4, 1 over rad 2. So it is also just rad 2. And then y of pi over 4 is tangent of pi over 4, which is just 1. So my point is rad 2 comma 1. So what is my equation of the tangent line? Y minus y1 is equal to slope rad 2 times x minus x1, or x minus rad 2. So here, if I wanted to solve for y, not that we necessarily have to, I would get, let's see, rad 2x minus 2. So if I distribute, rad 2 times rad 2 is 2. And then I would add 1 to the other side. So I get y equals radical 2 x minus 1. So that was the process without eliminating the parameter. So keeping it a set of parametric equations. Now let's first eliminate the parameter. So if we look at our equations, x equals secant t and y equals tangent t, when trig functions are involved in the parametric equations, we want to think about any known trig formulas that relate the functions. So secant t and tangent t, the equation I should be thinking of is the fact that tangent squared t plus 1 is equal to secant squared t. So now we know this is true from our Pythagorean identities. So now secant is x and tangent is y. So this equation would become y squared plus 1 is equal to x squared. What we have now is a Cartesian equation, an equation in x and y. And we want to move forward with taking the derivative. Now this is an implicit equation. And I'm going to go ahead and find the derivative using implicit differentiation. I'm going to take d dx of both sides and then go from there. So the derivative with respect to x of y squared, that's 2y dy dx. The derivative of 1 is 0, and the derivative of x squared is 2x. So to find dy dx, I'm going to divide by 2y, and I'm going to simplify at the same time. So dy dx is just x over y. But I want dy dx at t is equal to pi over 4. All right, well, what? I can't plug in t here. So what I have to do is remember that x was secant t and y was tangent t. So if I substitute in pi over 4 into secant t, we actually already did that. We said secant of pi over 4 was rad 2, so we get rad 2. And then if I substitute pi over 4 into y being tangent t, tangent of pi over 4 was 1. So there's my slope, rad 2, which we already know because we did this another way. And then I need x and y. Well, I need, again, x of pi over 4. Well, that was secant of pi over 4, which was rad 2. And y of pi over 4 was tangent of pi over 4, and that was 1. So my point, as we already know, was radical 2, 1. And so we plug it into our point slope form. Y minus 1 equals slope rad 2, x minus rad 2. So we get the same equation, right? So obviously we can do the same thing and solve for y. Y equals rad 2x minus 1. So one way was without eliminating the parameter, and the other was first eliminating the parameter. In this remaining part, we want to go ahead and do things like find the area under parametric equations, or find the arc length or surface area of revolution, but given parametric equations. So to start with, to find the net area under the curve with parametric equations, x of t and y of t, we're going to compute the following definite integral. The integral from t equals a to t equals b of y of t times x prime of t dt. So we want to note, when a curve is below the x-axis, areas are signed negative as expected. And as you go from t equals a to t equals b, The curve must be traversed exactly once. So what that means is that because our parametric equations can define some really interesting curves, we want to make sure that we don't kind of loop back around. So we want to make sure the curve is really just traveled over exactly one time instead of kind of going back and forth, back and forth. For this example, I want to find the area under one arch of the following curve called a cycloid. Here are the parametric equations. I have x equals 2 times the quantity t minus sine t, and y equals 2 times the quantity 1 minus cosine t. Here is the net area formula, and notice that the limits of integration are t values. So what I want to do is find the corresponding t values when this cycloid is touching the x-axis, because if I'm trying to find the area under one of these arches, it's between this time here, time A here, and time B over here. But this isn't necessarily time zero. Just because I'm at the origin, what that means is that the coordinate point xy is 0, 0, but that's not necessarily when t is equal to 0. So I have to find this t value here and then this t value here. And so at this coordinate point, I don't know what the x value is, but I do know that the y value is 0 because it's on the x-axis. And that's going to be key to finding t equals a and t equals b. The fact that the y coordinate is going to have to be 0 when the cycloid touches the x-axis. So in order to solve for a and b, what I need to do is let y equal 0. So 0 equals 2 times the quantity 1 minus cosine t. Well, here I can just divide by 2, so I'm really solving 0 equals 1 minus cosine t, or when is cosine t equal to 1? All right, when is cosine t equal to 1? Well, cosine of 0 is 1. That's one answer. But it's also going to happen again at 2 pi and 4 pi and 6 pi and so on. And then it'll actually happen at negative 2 pi and negative 4 pi and negative 6 pi and so on. And so hopefully we can kind of see based on this graph that those t values, there's going to be infinitely many of them. But if we're only trying to find the area under one arch, then we just need t equals 0 and t equals 2 pi. And so we can just quickly kind of check here. If I let t equal 0, I'm going to have 0 minus sine of 0, which is 0. So x is 0. And then 1 minus cosine of 0. Cosine of 0 is 1. 1 minus 1 is 0. So yes, it does turn out that this is t equals 0. And then t equals 2 pi. We know the y value is going to be 0. If I substitute in 2 pi into t over here, I'm going to get 2 pi minus sine of 2 pi. That's 0. So 2 times 2 pi is 4 pi. So this x value right here is going to be 4 pi, but that's not what I'm interested in. I'm interested in the t value when that happens. So my limits of integration are going to be 0 to 2 pi. So let's go ahead and start our area setup. So my net area is going to equal the integral from 0 to 2 pi of y of t. So this function here, as is, 2 times the quantity 1 minus cosine t, and then times the derivative of x prime of t. So I can go ahead and leave this constant multiple 2 there, and the derivative of t minus sine t, that's going to be 1 minus cosine t dt. And to solve this, we're going to need a little bit more space. All right, so 2 times 2 is 4. We can pull out the constant multiple 4. So 4 times the integral from 0 to 2 pi. And what we're going to do is we're going to multiply 1 minus cosine t times 1 minus cosine t. And that's going to give us 1 minus 2 cosine t plus cosine squared t dt. So we distribute it out there. And now cosine squared t, we're going to use the power reducing formula on. So I have 4, the integral from 0 to 2 pi, 1 minus 2 cosine t, plus cosine squared t, we can think of as 1 half plus 1 half cosine of 2t dt. And 1 1/2 are uh, like terms. So 1 1/2 is 3 halves. So let's see, we're going to have 4 here, and then I'm going to start to find the antiderivative. So 1 1/2 is 3 halves, so we'd have 3 halves t. The antiderivative of -2 cosine t is -2 sine t. And then the antiderivative of 1 half cosine of 2t, well, another 1/2 is going to pop out of there. So I'm going to have plus 1/4 sine of 2t. And this is evaluated from 0 to 2 pi. So now we're going to substitute in 2 pi into all the t's and then 0 into all the t's. So we're going to have 4 times 3 halves times 2 pi minus 2 sine of 2 pi. Well, that's 0. And then 1/4 sine of 4 pi. All right, well, that's also 0. Minus, now if I plug in 0 everywhere here, I'm going to get a bunch of 0. Sine of 0 is 0. So just minus 0 here. So what all is left? Well, here, 3 halves times 2 pi is just 3 pi. So I'm going to have 4 times 3 pi. So I'm going to have a total of 12 pi. So this is the area under one arch of that cycloid. Now let's talk about arc length given parametric equations. So the arc length for x of t, y of t, from t equals a to t equals b, is the integral from a to b of the square root of dx dt squared plus dy dt squared dt. Note that as you go from t equals a to t equals b, the curve must be traversed or traveled exactly once, so we don't want it to go back and forth on itself. On this example, we want to find the arc length, where t values range from 0 to 4, for the curve with parametrization, x equals 3t and y equals 2t to the 3 halves. So we're going to use this formula here. We are given our t values, t equals a to t equals b. So we just need to find dx dt and dy dt. So here, off to the side, I'm going to go ahead and calculate dx dt, just the derivative of x, that's 3. And then dy dt, using the power rule, 3 halves times 2 is just 3, so 3t to the 1/2. So we'll set up our integral. We're going to have the integral from 0 to 4, the square root of 3 squared, so dx dt squared, plus dy dt squared, so plus 3t to the 1/2 squared dt. Let's clean that up a bit. We're integrating 0 to 4, the square root of 9 plus 9t dt. So here, 3 squared is 9, t to the 1/2 squared, 1/2 and 2 multiply together to just be 1. Here, notice I can factor out a 9. And so if I factor out a 9 underneath the radical here, it's like 9 times the quantity, 1 plus t. And then I can take the square root of 9 now that this is a product, which is 3. So basically, I can rewrite this as 3 times the integral from 0 to 4 of the square root of 1 plus t dt. So just so it makes a u substitution a little bit nicer to work with, I can let u be 1 plus t, du is then dt. I'm going to change my limits of integration on over to u's. So u of 0, well, that's just 1, 1 plus 0. And then u of 4, 1 plus 4 is 5. So my new integral will be 3, the integral from 1 to 5, of just u to the 1/2 du. And then u to the 1/2, if we do the antiderivative, that's u to the 3 halves times 2/3. There's that 3 in front. And then evaluated from 1 to 5. Remember, we're not going to plug our u back in because we changed our limits of integration to u's. Let's cancel out these 3's. And so we're going to leave our final answer as 2, and then we'll plug in 5, 5 to the 3 halves, and then minus just 2, because if I plug in 1, 1 to the 3 halves is 1, so just minus 2. So I'm going to go ahead and leave my exact answer like that. If I want an approximate answer, it's about 20.36. So here is my arc length when t values are between 0 and 4 for this set of parametric equations. In this example, I want to find the length of one arch of the cycloid that has parameters x equals t minus sine t and y equals 1 minus cosine t. So this is very similar to the cycloid from earlier, except that the parametric equations were multiplied by 2. So here, in order to use this arc length formula to find the length of one arch, I'm going to need my t values that correspond to when the arch is touching the x-axis again. So I want to know at what t value uh, does my arch touch the x-axis. So we know the coordinate points are 0, 0 here, and then some number comma 0. So once again, the y value has to be equal to 0 in order to find the t equals a and t equals b. So once again, I need to let y equal 0 to find these t values. So 0 must be equal to 1 minus cosine t, or cosine t must be equal to 1. The same equation from before. So t must be 0, and then we have to go all the way around the unit circle again. So 2 pi and 4 pi and so on. But the relevant values for us are, once again, 0 and 2 pi. So those are going to be my limits of integration, 0 and 2 pi. And then I need to find dx dt and dy dt. So I'll do that as scratch work off to the side. Dx dt is going to be 1 minus cosine t, and dy dt is going to be just sine t. So the derivative of cosine is negative sine, so this is going to be just sine t. So we will set up our integral. We're going to have the integral from 0 to 2 pi, the square root of 1 minus cosine t squared plus sine squared t dt. And so just take a look at how this formula is similar to our traditional arc length formula as well. That was the square root of 1 plus f prime of x squared. So when it's parametric, it's dx dt squared plus dy dt squared. Now, we're going to need some space in order to solve this. All right, here we go. We have the integral from 0 to 2 pi, and I'll put a big square root symbol. Underneath that square root, if I distribute out 1 minus cosine t times 1 minus cosine t, I'll have 1 minus 2 cosine t plus cosine squared t plus the sine squared t there. And now let's observe that cosine squared t plus sine squared t, they're both positive, so that's going to equal just 1. Now we have the integral from 0 to 2 pi, the square root of 2 minus 2 cosine t dt. So if we go ahead and combine the 1 plus 1, we get 2. And now I could factor out the 2. And what I can do, in fact, is pull out a radical 2. So if I factor out the 2 and then take it out of the radical completely, and actually even take it out of the integral completely, how about we write it as radical 2, the integral from 0 to 2 pi, the square root of 1 minus cosine t dt. So now let's remind ourselves that we can rewrite 1 minus cosine t, the part underneath the square root here, using a power reducing formula in reverse. So I'll kind of show that work off to the side for a second. We know that sine squared x is equal to 1 minus cosine of 2x over 2. Let's go ahead and multiply by 2. So 2 sine squared x is equal to 1 minus cosine of 2x. Okay, but I don't want 2x, right? I just want a t here. So I'm going to go ahead and make a substitution. How about I let x equal t over 2? So if I replace this x with t over 2, I have to replace this x with t over 2. So 2 sine squared of t over 2 is equal to 1 minus cosine of 2 times t over 2. Well, the 2's cancel. So 1 minus cosine of t is 2 sine squared t over 2. So let's replace this part underneath with 2 sine squared of t over 2 and see what happens. So we have the square root of 2, the integral from 0 to 2 pi, the square root of 2 sine squared of t over 2 dt. All right, well, the square root of 2 times sine squared of t over 2 means I could take the square root of 2 out and multiply it times this rad 2, so I'm just going to get a 2 there. 2, the integral from 0 to 2 pi, and then here the square root and the sine squared cancel, and so I really just have sine of t over 2 dt. We need a bit more space. All right, so we have 2, the integral of sine of t over 2, that's going to be negative, and then this is a 1/2 in the front here, so the reciprocal of that is 2. So we're going to have negative 2 cosine of t over 2, and then evaluated from 0 to 2 pi. So we're looking at negative 4 cosine of 2 pi over 2 minus negative 4 cosine of 0. So 2 over 2 is going to cancel. So we're going to have negative 4 times cosine of pi, which is negative 1, minus negative 4, so plus 4. Cosine of 0 is 1. So we're going to have 4 plus 4, which is 8. We want to be really careful there. If we don't keep track of the signs, we might have ended up with 0, but that wouldn't make sense because we could see there was a length to that arch. And so that length is 8. And the last application to do with parametric equations is finding surface area. So the surface area for the curve x of t, y of t from t equals a to t equals b, when revolved about the x-axis, is the integral from a to b of 2 pi y times the square root of dx dt squared plus dy dt squared dt. And when revolving about the y-axis, it is the integral from a to b of 2 pi x, the square root of dx dt plus dy dt squared dt. So once again, note as you go from a to b, the curve must be traversed or traveled exactly once. In this example, I want to find the area of the surface generated by revolving x equals cosine t, y equals 1 plus sine t, where t values extend from 0 to 2 pi about the x-axis. So we're going to use this formula here. We have our t values, t equals a to t equals b. So we'll start the integral from 0 to 2 pi of 2 pi y. Now we're going to write the equation for y, 1 plus sine t. So our integrand is a function of t. We're integrating with respect to t. So we'll put 1 plus sine t. And then we're going to have the square root of dx dt squared plus dy dt squared. So here, I'm just going to go ahead and find and fill these in at the same time. So dx dt squared, the derivative of cosine t, is going to be negative sine t. So we're going to have negative sine t squared. So this right here is my dx dt, plus what's going to go here is dy dt squared. The derivative of y, well, the derivative of 1 is 0. The derivative of sine t is cosine t. So we're going to have cosine t squared dt. All right, so underneath this square root here, negative sine t all squared, that's just sine squared t. So what I really have underneath here is sine squared t plus cosine squared t. And we know that that is just 1. So this whole thing is the square root of 1, which is just 1. So our integral is going to be, I'm going to pull out the multiple 2 pi, so 0 to 2 pi, of just 1 plus sine t dt, because again, this whole thing is just 1. So we'll need a little bit more space. Now here we'll have 2 pi. The antiderivative of 1 is t. The antiderivative of sine t is negative cosine t. And we're evaluating from 0 to 2 pi. So I'm going to keep the 2 pi on the outside, and then I'm going to substitute in 2 pi minus cosine of 2 pi, minus 0 minus cosine of 0. So I want to be careful and keep parentheses around this quantity here. And then let's go ahead and simplify. So we'll have 2 pi, we have 2 pi, and then let's see, cosine of 2 pi is cosine of 0, which is 1. So we have minus 1. And then here we're going to have minus 0 and then plus cosine of 0, which is 1. So we're going to have plus 1. Well, minus 1 plus 1 is 0. So all I have left is 2 pi times 2 pi, which is a total of 4 pi squared.